So we want the volume bounded by the region, and not necessarily like we're not doing
the
we're trying to use right. We're trying to use a triple integral, not a double integral. In the case of the double integral, I think we could attack it like that, but I don't know. I'd have to write it out.
Okay, yeah, I think I get it.
Yeah, I think the goal is that we're taking the triple integral of one over the region with the goal of, or over the I don't know, the region that we're concerned with the goal of finding the volume of the region.
Calculus 4 is on your mind. I like it.
Yep.
Good stuff.
David, did you say the volume when we take a triple integral?
Yeah, the triple integral of one is the volume of the region or the domain that you're integrating over.
Isn't the triple integral the one that's a 4D object or a 4D concept?
Right. So when you triple integrate a function of 3 variables, then it's like a 4-dimensional thing. But the analogous case is the double integral of 1 over the region gives you the area of the region that you're concerned with, and the triple integral of 1, over the region, the 3-dimensional region is the volume of the region.
We'll talk about this later. I think I got something for you.
Okay.
So cool. That's the awesome. All right. So looking at the syllabus, as I mentioned the other day, we are not doing 7.4 only because 7.4 is, again, a precursor to solving differential equations. And I already showed you how to solve them, and I intimated that the difficulty is kind of decomposing what ends up on the right side back into something that you recognize from the Laplace table. So rather than spending a bunch of time practicing that, let's just get into it and solve it. We got 3 days set aside to kind of do this because it takes a long time to solve one of these, and we just got to get better at kind of decomposing what's on the right side. So again, these are really cool because you can solve any differential equation using this without really having to think too much, but you just got to be kind of awesome at algebra, or at least practiced in the art of recognizing the Laplace transform kind of in the table that we began making. And so let's start with something that we once did one way, and actually want to take the time, because I think this is a good place to take the time to kind of solve a problem we used to do a different way. So if I said y prime on a previous test plus 3y equals 5t on a previous test, you would say, oh, first order differential equation. And you might look at that and say, okay, I can't separate that. Remember, we had to look at this and go, okay, is it separable? And we always kind of liked that one because it was easier. But if it wasn't separable and it was linear, which is what this one is, then we said, oh, okay, that's the mu technique. And so at the time we said it, and this was already kind of set up for mu, this multiplier. And we found it, if you recall, by saying mu will be equal to e, is this right? I'm trying to remember. To the integral of whatever this function is right here. And it's very important that there's a 1 in front of that. So if there was something in front of the y prime, remember we had to divide it away. And so fortunately, this is just the integral of 3 with respect to, and notice we know the independent variable is t because there's 5t on the other side. So we don't kind of have a choice. Sometimes we can just pick x. So we would say then that our mu then is just e to the 3x. And we said, miraculously, if you just took that brilliant discovery there and then you multiplied everything through by e to the x, since you know and love the distributive law, I'm sorry, t, not x. After I just got done making that speech, I failed my own test. And so we said that made progress. Now, somebody put quickly into words, why is that kind of cool? Because it looks just like way worse and terrible. And remember, we're thinking long term here, not just, one time I knew this. But what's really cool about what's sitting right here now?
It's the end result of the product rule.
Yeah, that is the product rule having been taken. Thank you, Ben. In other words, And I actually don't have a super good feel if you're all like, yeah, we totally know that it's easy, or whether and we don't want to say anything, or whether you're like, geez, I forgot. In other words, if you took that and took the derivative of it, it would indeed produce what's above it. And notice it really did work, because the derivative of, man, geez, I gotta wake up this morning. I said mu is e to the 3t, and then I went in there and didn't throw any of those threes in. The derivative of e to the 3t really is 3e to the 3t. And so, yeah, that worked. I mean, that's why this kind of mu trick was sort of cool. It worked. So great. And then, of course, the brilliance of that is now I can take the integral of both sides. And since integrals and derivatives cancel each other out, fundamental theorem of calculus, then I have this. And notice I'm, in a sense, the beauty of this is, hey, look, we all this time we were in this entire class, we've always said, hey, in the real world, we're stuck with an equation that has a derivative in it. Like we were stuck with the beam with an equation that has second derivative in it. And so we got to get rid of that. We got to take the integral, and notice we did that here. And so we've got y. All we have to do is, well, figure out what y is equal to. And unfortunately, on the right side, that's not a super simple integral to take, but you should be able to see that that is integration by parts over there. And so I can survive this. I'll do this kind of quick. So if this is u, then when I take its derivative, u prime will be 5, and that'll make it kind of go away effectively. And if this e to the 3t, that I forget the 3t, if that's our v prime, then that means v would be 1/3 e to the 3t. And so we said, okay, great, leave the left side alone. We look at the right side and we say, I can't do that integral because it kind of looks like product rule, but we say by integration by parts, that's the same thing as uv 5 times 1/3. Remember, uv is often ugly, but we don't care because we don't have to take its integral, minus what we're hoping is a newer, easier integral. And so the integral, though, is of u prime v, and because that's 5 times 1/3 e to the 3t, notice it's not, well, two things multiplied anymore. Of course, we can move this 5/3 out front, just so we don't get confused. And then we say, okay, yeah, that integral is easier now. It's the beauty of integration by parts. And so I can take the integral of 3t. And so great, I'm home free. And so awesome, 5/3 t e to the 3t minus the integral of e to the 3t would be e to the 3d divided by 3. So that would become 5/9. And so then I've done it. All I have to do is divide by e to the 3t, which beautifully causes a lot of this to simplify. And so this would be right, except for what huge mistake have I made that you cannot afford to make here? In other words, the answer to this is a line. Well, it isn't a line. What huge mistake have I made that none of you are making anymore? You used to make this mistake, but you never do now.
Constant.
Yeah, when you take the integral plus c. And notice how profound that is, because when you divide that constant by e to the 3t, I'm going to write it as e to the negative 3t, just so I don't have to write fraction there. That's going to be a very interesting term, right? I mean, you can tell the graph now is no longer just a line. It's like a line plus an e. And so this is a really interesting equation. So let's see. Assuming I haven't made any dumb mistakes, we say great. But remember, that was very specific. There's a lot of things I had to know to pull that off. I had to recognize it was linear so that I knew to use this technique, and then I had to do integration by parts. And that was a technique that worked in this, kind of tiny environment. And so now we're saying, what would I be doing if I just did integration? If I just did a Laplace transform. Now, just to make this kind of look a little nicer, let's go back to the start and throw an initial condition at this. And notice I said initial condition, not conditions. There's only one unknown to this. And when you have an equation that's a first order differential equation, then the only thing you know is its initial position. So at time 0, this thing is equal to 6. I'm just kind of making that up. And so let's finish this down here and say, okay, y is 6 when the time is 0. So that makes that 0. This is -5/9. E to the 0 is 1. And so that makes C equal to 6 5/9. Which I guess is 54, 59/9. Is that right? So then I suppose I could say, finally, and I could say, now I have my particular solution to this. And so there was a time when that was our method. But what we want to know is, like, what would happen if we just said, that's what's so cool about Laplace transform. It doesn't matter. If you see a derivative in an equation, just take the Laplace transform on both sides. And what we started to see on Thursday was that really what a Laplace transform does is take a derivative away, because after all, isn't a Laplace transform an integral? And that's kind of the beauty of its creation. So in a sense, this is the old way. And again, I'm actually not here to say, old instead of old school, bad, like that's a terrible way. Not necessarily. It has pros and cons. I wish Laplace transform was just, easy. The only thing really easy about it is I don't have to recognize this as a linear equation. I don't have to know integration by parts. I just take the Laplace transform both sides. So what does Laplace, Simone Pierre Laplace, have to say about this? About y prime plus 3y equals 5t with the initial condition y of 0 equals 6. So we say, okay, great. Let's take algebraically, as we like to do, let's take the Laplace transform of both sides. And we like plus signs. Integrals like plus signs. It's all Laplace transform is. And so I'm very happy to see the plus sign between 3 and y. So the Laplace transform of y prime, what did we say that was? And on the test, this is what you should be doing. Perhaps you have, things memorized at some point, but even if you did, it would be smart to, let's make a mess of these things. It would be smart to kind of double check on this sheet, just so that you don't do something silly. So you say, okay, what's the Laplace transform of a derivative? Oh, it's S times the Laplace transform without the derivative. So the derivative is gone, minus the initial condition. Okay, that's right. You say, I knew that. So S times the Laplace transform of our function, which is y, minus y of 0. I think I'll go ahead and write y of 0 first. So there's the Laplace transform of y prime plus 3 times the Laplace transform of y equals the Laplace transform of 5t. And I could even write, I think I will, we said that the constants can just be pulled out front, which is why I pulled the 3 out in front. I didn't say the Laplace transform of 3y, although you can, that's fine. But we said that pulls out front. And again, convince yourself that's okay to do, because the Laplace transform is just an integral. So I could put this 5 out front and say the Laplace transform of t. And so there, I took the Laplace transform of both sides. So what do I get as a result of that? Well, that is 6. And then, the Laplace transform of t, that's right, we built that. Again, maybe you have that memorized. Good for you. Double check anyway. What's the Laplace transform just of t? Not t squared, not t cubed. That'd be the one below it. It's just 1 over s squared. So we made this in the table. We made it once. Let's not make it again. It's kind of the idea. But again, I would encourage you to, as I said before, have your own table. Don't just use mine. Like, make your own. It's actually kind of cool that you can own these for yourself. You can build these all by yourself. It's kind of powerful, I think. So it's the wrong note. So the Laplace transform of t is 1 over s squared. And again, what's the beauty of this? I mean, it looks really terrible, but do you understand what we didn't like before that was important, that made us recognize this as linear? Is here's this function that I don't know what it is. You know, remember, it could be sine of e of x or e of t or something. I don't know what this function is. And here's its derivative. What's the beauty of a Laplace transform? It's like, I don't have the function in its derivative. Notice I just have the Laplace transform of y and the Laplace transform of y. It basically takes derivatives away. That's what's kind of cool about it. So now I say, okay, well, on this left side, I could now factor out the Laplace transform of y. And of course, we're not going to be able to find out what the Laplace transform, the important part of this technique is, we can't take the Laplace transform of y because we don't know what that function is. Remember, we're hunting for a function in this course, y, and we don't know what it is. And so we're not going to be able to take the Laplace transform of it. The only thing we can really do is write it down. And so if I factor it out of these two terms, then doesn't that leave an s and a plus 3? And on the other side, I have 5 over s squared. And I would have had to have added this 6. I would have had to add this 6 right here to the other side because it didn't have a Laplace transform of y. Hopefully algebraically, you're like, yeah, you're boring us. That's easy. And so, awesome. Now what's my next move? Well, really just solve for the Laplace transform of y. Divide everything by s minus 3. I think to clean things up a little bit before that, though, maybe I'll find, I don't know if this will be helpful or not, but maybe I'll add those two fractions on the other side together, get a common denominator. So this would be 5 plus 6 s squared over s squared. I'd have to multiply the 6, obviously, top and bottom times s squared. And so now I'm going to divide by s plus 3. And so I can say that the Laplace transform of y is equal to 5 plus 6s squared over s squared times s plus 3. And so 7.4 that we're skipping basically says, take a look at that creature that this just made. And it's kind of like, now the problem becomes like, ultimately the Laplace transform is pretty easy up to this point. The question is, you know, how do I decompose that? I mean, does that look like anything on the chart? That's kind of the idea. It's the big picture question here. If I go to, again, my table is just a little smaller than the other one, which I think I posted. You know, I'm just looking for, you know, is there any of those? Is there any, do I see that over there? Do I see this over there? Do I see, you know, something looks like that? Do I see s minus a? Oh, yeah, s minus 3. S minus 3, maybe there's an e in it. I mean, that's what I'm thinking, right? I'm just trying to get it to look like things on the right side, but it doesn't, and it doesn't yet, and it's kind of a long way from doing that. And so one of the key techniques that you saw Thursday when I showed you this is to recognize that this expression here will separate. And so we're going to decompose this fraction. In other words, is there some, could I think of this as like a fraction that I added since I recognize those two denominators, those two separate denominators? Is there like something over s squared plus something over s minus 3 Do you see how that would be progress?
Would we need like a C over S term?
Yeah. And so we gotta talk more about like what, and this is not simple. And that's why, the author was not wrong to say we need a 7.4 here for them to kind of practice this a bit. I totally get why they did that. I just think it's because if you don't see these in context, it's just hard to understand, like, why are you telling me how to do this? I mean, I think of it as like teaching people how to tie rescue knots when they've never, hiked in a crevasse or, something of that nature. It's like, you got to kind of see the danger and see, why it's important before you're going to pay the right kind of attention. But do you see that now, at very least, like these two statements actually look pretty familiar? Junk over S squared, wasn't that the Laplace transform of T? And junk over S minus 3, wasn't that E to the 3T? And so, like, if I could pull this off, that'd be awesome. Do you see what I'm saying? So you're always looking for composite, kind of a composite expression down here. But the art of this, as David kind of pointed out, is, like, what do I put up here? And that's not so easy.
Is it supposed to be B over S minus 3?
No,
Or
plus.
S plus 3?
Yeah, I was just idiot.
Doug, oh, sorry. Do you, I was trying to look for the note sheet, but I couldn't find it.
Did I not
You know,
post
you
it?
posted it? Maybe not.
Is that true? Did I not post it? Because I'd like to quickly do that right now, just so you can all have it. It won't take me just a second to do it. So I'll go look really fast. Apologize.
I've just been using the one online.
So I'm posting it right now in the course information.
Cool. Thanks.
Nice.
Fine. File, show always, choose file. Okay, it's in there. And I'll keep referring to it here. But what I would like to do, because again, you've seen before that my overall goal is not to teach you this stuff mechanically, but to really give you a chance to think. And so let's kind of try something here that maybe isn't going to work so good. And so, David's question was like, is that going to work? And, maybe he's read ahead and was kind of looking at some of the details, but let's try to add these and see if we can get this to work. And so let's see. If this was the case, I would have to multiply this one top and bottom by S plus 3, this one top and bottom by S squared to get a common denominator. So the question is, will that actually work? And so we would say, okay, well, then that would be AS plus 3A plus BS squared over our denominator, S squared times S plus 3. And so the question is, can I get this? Are there values I can pick for A and B that will give me what I need? I need a 5 plus a 6S squared. So I say, well, the only way that's going to happen is, since I only have an S squared term, does it make sense I automatically know B has to be 6? Because then I would have 6S squared. Great.
A has to be 0, but it can't be.
Why does A have to be 0? You're correct.
Because there's
right?
no S term up there.
Yeah, look, there's no S term. So you'd have to make A equal to 0. But then over here, we need A to be 5/3, don't we? We need A to be 5/3 so that it can produce this 5 up here. And so we have a contradiction. Like, there isn't a way to make that happen. Do you see the issue there? And so, and this, again, this is what 7.4 is about, is like, how do you navigate that? So So I'm going to show you one way out of it right now. So I'm teaching you 7.4 just in the context of actually solving problems. So we tried this. What if we now try something else? Well, how would I get that to go away? Well, one idea I'm wondering about is maybe if I added an S to this, or maybe even a plus C or something here. You know, I don't know, like I can, it doesn't have to just be a constant. So I don't know, let's just try adding an S and see if that happens. So I'm going to write up here, impossible. Again, what I'm modeling here is playing. I mean, you're the kind of person that just wants to be told. And I actually don't have a problem with that. You just want to go look at 7.4 and, you know, find a technique. Give me the technique. Tell me what to put in there. You know, it's like, let's get on with it. That's okay. But you know, real mathematics or real mathematicians are people that, you know, discovered this stuff. And so, like, what's wrong with playing it? To me, it takes the fun out of it if you're just told exactly what to do, especially if it's within your capacity to do it. So let's just try the same thing again. Will this get us out of our mess? So this would need an S plus 3. This would need an S plus 3. This would need an S squared. This would need an S squared. And so what would I have then? I would have AS times S, A S squared, and then 3AS, and then BS squared. And so awesome.
Hey, Doug, if you put an S on the top, would you have to put it on the bottom? Would that become S cubed or?
No, because there's really no, what we're trying to figure out is basically what to put up here. In other words, you know, when I put A up there, it's kind of like, oh, A is a constant. Well, does it have to be a constant?
Oh, I see.
I'm basically saying that maybe not. Like maybe it's a constant times S.
Gotcha.
So
Gotcha. Okay.
I'm just playing, I'm just guessing right now. I'm just trying to come up with something. Is this going to work?
It could.
Should be able to tell me by looking. Is that going to work? Remember, what am I trying to accomplish? I'm trying to
There's
get
no constant
this.
term up there.
Yeah, I'm trying to get this to equal what it's supposed to equal, right? But notice there is no constant. Because I threw that S in there, there's no constant. So it looks like I could get, you know, AS squared plus BS squared to be equal 6. But notice again, because this is an S term, A again has to be 0, which means B has to be 6. And that actually works now, except for I don't get the 5. So this didn't work either. Let's try a third one. What if I gave that term an S kind of and a constant? So now it's like a line. Does that make sense? A second ago, it was just a constant when I tried A. And then when I threw an S in there, it was like a line that didn't have a y-intercept, but it's just, I'm giving myself more latitude now. Does that make sense? I have more options. So maybe this will work. or, maybe I should put a S by B. I don't really know. I'm just kind of playing around with things that I could pick. And so again, let's see what happens. So if I multiply this by S plus 3, multiply this by S squared, then I get AS times S, AS squared, AS times 3. So I get 3AS. And then I get C times S, and C times 3, and then B times S squared. So do you see what I'm saying? Like I have more stuff to work with now. Maybe now I can get everything I need. What are your thoughts?
I think that fixed it.
Yeah, so notice there's like, where should I start? Should I try to get S squared first? Your gut reaction to that should be, well, that's not so easy because BS squared plus AS squared would have to be 6, but that is, I don't know what A and B are. It could be 1 and 5, could be 2 and 4, it could be 1 and 6 and 0. I don't really know. Is there any place I can start? Can I start with S? Notice there's no S terms up here. Can I start there? The answer is not really, because 3AS plus CS. So I know that 3A plus C has got to be 0. But again, I don't know which one. But then there's this constant term. That one I know for sure right now. That's the only constant term up here. And that's kind of cool. Putting that C there actually gave me a constant term, which I didn't have in the previous problem. And so this is actually looking pretty good. And so right now, thanks to this, I know that C has to be 0. Wrong. C has to be 5. Or whatever C would be to make 5, which would really be 5/3, right? 5/3 times 3. So I know C right now has to be 5/3. Well, then notice the domino effect. Then I could say, well, if that's true, then I know that 3A plus C has to be 0, since there is no S term up there. So 3A plus C has to be 0. But now I know C is 5/3. So that would mean 3A is negative 5/3, and that would divide by 3, and A would have to be negative 5/9. Or any bells ringing in your mind? Hey, didn't we have an answer like that?
Yeah, we've seen those before.
5/9. We see that before. And now that I know A, my sort of domino effect is taking full effect, then I can say that A S squared plus B S squared has to be equal to 6S squared. And now that I know A is negative 5/9, then I know B is 6 5/9. That also sounds really familiar. 59. So I actually found, I was able to, if you will, kind of guess appropriately. Now, again, the word guess always bothers me. It's like the idea that I would want to study this and, make a whole chapter and really study how to not get this wrong. Like I got it wrong twice, right? I don't want to flounder like this forever. So I want to get systematic about this. So maybe one of our, solutions to this is, and I guess I'm just hypothesizing here, but like notice this was an S term, like S to the first power. And then this went down a degree. In other words, this is S to the 1, this is S to the 0. This is S squared, and this is S to the first. It went down a degree, but it also needed like everything below it. In other words, I'm kind of wondering in my head right now, like what if there was a S cubed on the bottom? Would I need like an AS squared plus BS plus C on top? Does that make sense? Is that what I would need?
I think that makes sense.
Kind of like that fits the pattern. You see what I'm saying? And so, maybe that's the answer. But the idea that I could kind of, get better at guessing so that I wouldn't kind of waste my time. And so I think I found this. And so wait a second. Now, what does all this mean? Like I kind of forgot what I'm even doing here. So that means the Laplace transform. So we can now say that the Laplace transform of y is now equal to not the ugly fraction it was before, But A, S plus C, we said A was negative 5/9, S plus C plus 5/3, and that was all over the top of S squared. And then B over S plus 3, but B was 59/9. So those are pretty ugly expressions, but do you see that, hey, look, junk over S squared. Now, as I said the other day, notice there's a 1 on top. Like we don't have a 1 on top. We have a 59/9 up there. So that's not good. However, it isn't a terrible jump to get that to be the case. And then the same thing is true for this one. Don't we have junk on the bottom? We don't have S minus A, we have S plus 3, but isn't that S minus a -3? In other words, A is -3. But again, there's a 1 on top, right? There's not. So what do I do? I don't have a 1 on top. I have like an S on top. Does that make sense? Does that kind of bug you a little bit? Like, oh, what are we going to do? What are we going to do with that? So we're getting warm is kind of the idea. It's kind of looking like these two, but I need 1s on top. And so, what am I going to do about that? Do you feel good about, well, this? Is this a good idea? Since those already have a common denominator, I mean, couldn't I split those apart? Do you notice, at least if I look at this one now, there's no S anymore. Now I'm looking at this one thinking, well, that's not going to work because, there's an S on top and there's not supposed to be. It's supposed to be 1 over S squared. But what did we say was kind of cool about integrals with respect to, if I have the integral of 5x and I'm like, oh no, what do I do with that 5? Well, didn't we say the 5 can just come out front? I mean, wasn't that one of our basic rules? We used it a little while ago. We said, what's the Laplace transform of 5t? And we said, well, the 5 can just kind of come out front. Well, that's what we're after here. In other words, we're actually pretty darn close now. In other words, I can take that 5/3 right there and say it's 5/3 times 1 over S squared. And now that looks perfect. I can stare at that and say, hey, that's awesome. Isn't that the Laplace transform of t now? Like I can say that for sure. It's perfect. And then can't I do the same thing with this? In other words, if I pulled the 5/9 over 9, kind of factored it out in front so that this is 1 over S plus 3, then isn't it now recognizable as the Laplace transform of e to the -3t? And again, notice it's S plus 3. So I'm thinking of it as S minus a -3 because it had to be a minus sign, right? It was S minus A, not S plus A, and that's important. And so I'm thinking, oh, that's a -3. Oh, okay, well then it's S minus -3. Well, then that means our A value in the Laplace transform is -3. But what about that first one? Who can help us?
Just pull the 5/9 out. I think there was 1 in there.
And cancel out the S on top and bottom.
Yeah.
Yeah. Now that they're split up, like you can't do it back here, right? You can't go cancel back there. But when I separated them, you can. So in other words, you could cancel them here, cancel that one, cancel that. So the question is, was that one? Was that a Laplace transform? Was that one of the ones we
Laplace
made?
transform of 1.
Yeah, that was the Laplace transform of 1. So what can we now say that's kind of cool? We can now say that I read our original problem, just going back up to the top. we can say the Laplace transform of y is equal to -5/9 times the Laplace transform of 1 plus 5/3 times the Laplace transform of t plus 59/9 times the Laplace transform of e to the -3t. Woo, barely squeezing in there. Why is that cool now?
Because you just factor all the, you just take away all the Laplace transforms.
Exactly. You undo them. Like the Laplace transform is just like an operation. It's like squaring something or cubing something or taking the derivative. You're just doing something to it. I mean, think about it this way. Like if I said, hey, what's the derivative of 9x squared? I mean, that's an operation that you do, right? If you told that to somebody that doesn't know calculus, if you said take the derivative of 9x squared, they're not going to know what you're saying. But really, it's just an operation, right? It's like it's something that you do. And of course, you could explain it to them. They wouldn't understand why, but you could say, all you do is just take this 2 here and multiply it by 9. So it becomes 18. And then that x to the second becomes x to the first. And so bam, you just transformed it into something totally different, right?
Is there a mathematical notation for un-Laplace transforming something?
Yeah. What is the generic? You tell me this. What's the generic way of undoing something in algebra? What's the generic statement? What do you say like for sine? What if you say, all right, I need rid of sine. I'm sitting here and I have the sine of x equals 0.7. And I'm like, I need to solve for x, which means I need to get rid of the transformation of taking the sine of a number. What do?
You raise it to the -1 power.
Yeah. Raising something to the -1 power. That's not wonderful, right? Because 5 to the -1 doesn't mean inverse. Like -1 got used for 2 different things. And so that's really annoying to me. I think there should be a different symbol for this. Could have been anything, frankly.
But does it not indicate like kind of like since squaring something is multiplying, or like raising something to an exponent power is multiplying by the number of times, so kind of the inverse would be like dividing.
Yeah,
sort of.
it kind of zeroes it out. That's exactly right. And that's why it was picked. It just would be good if it would be good if they'd come up with something different, or maybe use the negative. Don't use the negative for exponent or something of that nature. But the key is really now I just need to take the inverse Laplace transform.
Maybe it has to do with the notation with the parentheses. So like if you have like a squared and you want to like, I guess, subtract the 2, then you have like parentheses and you raise it to the -2. And so it kind of like inverts it sort of in the way that you would with a function if you were taking its inverse, like you would do like f inverse of f of x. I don't know. Anyway, sorry, that was just an idea.
No, that's good. And the idea of it being -1 does make sense, because if I say L -1 times L to the 1 times, I think it was times, like times y, doesn't this become L to the 0 power, which makes it 1, which makes it go away? I mean, that's the idea behind that symbol. That does make sense. I completely get why mathematicians invented that. But we just have to understand that, that does not mean 1 over Laplace transform, 1 over L, because we did use it for that in other places. And so that's a little bit annoying. My point is it could have been something like star, but you can see the logic of, it could have been L star, that means inverse. But you can totally see the logic of that. But the cool thing is just, if I see, as long as I have L everywhere, in other words, it wouldn't work. If this one wasn't here, then I can't do it. I need the plus signs and I need everything to be a Laplace transform for this to work. So I'm really excited about plus sign, because that means I can look at them all separately. But if I take the inverse Laplace transform, it just means that it went away. Just like the fundamental theorem of calculus. I'll take a derivative, that'll take an integral. Hey, you just got back where you started. Those are inverse operations. Well, it's no different than a Laplace transform. And so my point is you've been transforming stuff for years. You've been getting rid of square root by squaring it. You've been seeing those as inverse operations. And this is just no different. So the cool thing is we never even had to figure out what the Laplace transform of y was. We just figured out a way to get everything to be a Laplace transform. So now we just go back. So now I can say y is equal to -5/9 plus 5/3 t plus 59/9 e to the -3. And then it's like, what? That's the same answer we just got using a way radically different technique, right? Hopefully it is. Wow, that was a long time ago. Is that what we got? Anything wrong? I know all the fractions are right, but is there like a sign problem or anything? 5/3 t minus 5/9. Yeah, that's right. Wow. Now, what's your gut feeling on this? Do you think this is worth it? Like, would you rather just say, nah, I like mu, and I know I have to pay attention to that. Like, oh yeah, that's a special case, and I use mu. Or do you find yourself going, that's rad because I do the same thing to both sides, and like the example I did last Thursday was a second order differential equation. Remember, we had a totally different technique for that, totally different technique for a second order differential equation, and and then here's a first order one, and it's like Laplace transform just works every time. Do you like that, or do you find yourself going, yeah, but this is like a weird world and it's a whole lot of trouble? And actually, we'd kind of like to hear what some of you had to say. Just gut reaction. You might change your mind later. But
I think it's pretty cool because it looks like it works for everything.
Yeah. Somebody else, what do you think? You like it? Don't like it?
I think the transform part of it's pretty cool. It's kind of like I really liked when we brought in complex numbers, and for that same reason, I felt like we were extending what we could do, kind of like going around instead of, if you reach an obstacle, going around it instead of through it. I don't know, feels cool.
Yeah, well said.
This old control systems engineering handbook I looked at before I started the differential equations class, and there was a lot of Laplace transformation stuff that it talked about, and I'm gonna look back through that book after this class.
Yeah, you actually
I might
understand
know some of it now.
a little bit about what that means.
They use something from control theory, quote unquote, in the book as an example for a place where you can use a Laplace transform.
Yeah, as it turns out, I mean, there's a ton of real applications for second and first order differential equations, and that's because we're able to write an equation based on how something is changing, not about the thing itself. And so the only equation we're able to write down is change, and then we say, okay, well, that isn't what I'm after. I'm after, this is y as a function of t now, which means if I pick any time I want, I now know what y is, and if y is the amount of lead flowing into the lake or whatever. I'm reading a book right now about these crazy people that decided they should sail their sailboat up to the Arctic and then just let it freeze over, because it's only like the glaciers and stuff up there, the lakes and the ocean are only unfrozen with icebergs floating in them for like 3 weeks, and then they freeze back up again. So they thought it'd be really good if we just had a bunch of supplies and we sailed up there and then just let our boat freeze in and just try to live through the winter, with no light. And it's a crazy story. They lived, or I guess they wouldn't have got the book written. But anyway, the only reason I mentioned that is they were talking about some of the mosses that were on the rocks, and Chernobyl was a nuclear accident. I want to say back in the 80s, but I can't remember how long ago that was. And basically, radiation just kind of went over half the surface of the earth, and that particular moss soaked it up. And so you can imagine being a scientist and saying, what's going on with this moss? I'm going to measure this. And you want to measure how the radiation is changing. And the problem is the animals eat the moss, and then other animals eat those animals. And now the Inuit people that were there had radiation in their systems too, as a result of the animals eating moss and so forth. And but you can imagine wanting to understand how that all works and trying to study it. And maybe all is an equation about change. But the idea that, well, maybe I'll use the Laplace transform, because what I really want to know, if y is like how much uranium is inside this person as a function of time, is that going to leach out over time and not affect them? I need this equation we put in a box. The change equation isn't going to do me any good. And so yeah, it turns out that most people lean on the Laplace transform as a way to solve these things. So let's just keep wading into this. So the one thing I just want to walk away with, and I also want to tell you, if you want to look at 7.4 in the book, like this is not the technique that they used. The technique I just used right there to come up with our guess, if you will. This guess right here, they don't use that method. And I'll show you that too. But I just think it's cool to kind of like flounder around and try stuff a little bit. So in a sense, we have a whole extra day here to kind of think about this, just so that we can play with it instead of me just saying, if you see this, do that. Because if I end up making like a whole set of rules as to how to kind of decompose this right side that develops, if it ends up this huge list of rules, then I kind of feel like, well, no, I don't even like this technique anymore. I just would like to see if I can think and reason about it a little bit. So I'm trying to decide what should I give you next now. You know, because part of me says, like, remember all the rules for solving different differential equations. And so, I mean, wasn't this, if we just stick to homogeneous to start with, isn't it weird that, you know, sometimes the equation was kind of simple and it was just e to the RT, but then sometimes there's like a t thrown in there, and then sometimes all of a sudden even trig showed up, right? Like that was kind of weird. And in our case, you know, at the time we kind of had, I don't know if memorized is the right word, but if you got two distinct different real roots in the auxiliary equation, then it was just an e equation. But if you got repeated roots, then you had to throw this little t in. But if you got complex roots, this is what David was alluding to earlier, then we said, oh, well, if complex roots, then, you know, now it's all of a sudden it's got a sine and a cosine in it, right? And so man, that's just like, how would that happen, like in this world? And the good thing about this world is we don't have to memorize those three different cases. We just kind of wade in and figure it out. But of course, that, you know, last case sort of feels complicated. So I'm kind of trying to decide, can I throw that at you right now, or should I save that a little bit? Maybe we'll save that for a minute. Let's just take a quick look at what I did with you guys last. What was this? So this is what we just tried a second order differential equation. And again, nice being that it's homogeneous, and because we got distinct real roots, that made it kind of come out fairly straightforward. But let's just try, like, what would happen if it wasn't distinct roots, right? Like, and again, we're not supposed to notice that. So let's see if we can just make up a problem right now. And I may, some of you are future math teachers, I may even kind of make this up live, but let's just do a second example. Let's do a second order homogeneous differential equation, except for, let's just kind of add the caveat. And the cool thing about this method is we don't necessarily have to notice this, but we want it to come out with repeated roots. And so does it make sense this would accomplish that? If I had y double prime, let's see, let's make it kind of simple. Minus 4y prime plus 4. Does it make sense that that factors to r minus 2, r minus 2? Didn't finish it. And let's just throw some totally random initial conditions at it, which is probably going to mean horrible fractions, but I don't think I want to take the time to show you how and you might think about this if you're a curious person, but on the test, I was able to choose values for, instead of 3 and 4, I chose values that made everything come out with nice whole numbers. You might think a little bit about, like, how did I do that? So the cool thing about Laplace transforms is you don't have to stare at this and notice, hey, this is repeated roots. But do you agree, based on what we did before, that this is the kind of answer we're supposed to get then? We're supposed to get that t right there. And so before this, we had to notice that. We had to recognize that and then, you know, consult our brilliant photographic memory or the note sheet. But how's that going to manifest itself in this world, right? Because what we're saying now is I just walk up to this thing and just bam, take the Laplace transform of both sides. Let's keep going. Don't do anything. Just take the Laplace transform of both sides. So I'm going to do this kind of systematically. I'm going to need the Laplace transform of everything. So let's do this in kind of an organized way. Well, what's the Laplace transform of y double prime? Let me see. I'm going to try to do it from memory. Wasn't it s squared times the Laplace transform of y minus s times the Laplace transform of y minus y of 0? Let me think to myself, and I'm just thinking out loud. It was like, no, that wasn't it. So, and again, this might help you. So the pattern that I kind of remember, was that you start with s squared, and then it goes down to s, and then there's no s's at all. And then here's where I recognize I made a mistake. Then you start with a Laplace transform, which is an integral, and then you take its derivative, which means it's gone. So I screwed that one up. So I took the derivative of the Laplace transform, which is an integral, and therefore it got rid of it. And then I take the derivative again. There we go. So by the pattern, does it make sense? I was able to bring that back. And I wasn't like acting that, like actually what I just wrote, what I originally wrote, I actually thought that was right. But I just got that back without looking at my note sheet. Now you should look at your note sheet on the test, but it's like, I think I got that right now. That's the pattern of these things. And so there's the Laplace transform of y double prime. Now we're also going to need the Laplace transform of negative 4y prime, which we immediately recognize the negative 4 can come out, so that all I really have to do is take the Laplace transform of y prime. So I can't forget about the negative 4, and then the Laplace transform of y prime is s times the Laplace transform of y, and then minus, like we saw a minute ago, y of 0. And I don't really need to write this down, but just to be consistent, then the Laplace transform of 4y is just 4 times the Laplace transform of y. So there's all my junk. So I just write all that out. So fortunately, this, y double prime wasn't multiplied by anything, so I can just kind of rewrite that. And then I got to multiply 4 into the next one, so it'd be minus 4s times the Laplace transform of y. Minus 4 times minus y of 0 would be plus 4 y of 0. And then plus 4 Laplace transform of y. And that equals 0. And again, it's important to remember that we decided the other day the Laplace transform of 0 is 0. I didn't say it equals 0 because it was 0 on the other side. I had to take the Laplace transform of both sides, right? So if there had been like a 2 over there, look at your chart.
2 over s, right?
Yeah, exactly. If there had been a 2 over there, it wouldn't have been a 2. It would have been the Laplace transform of 2, which is actually 2 over s. And so that would have made it messy. Does that make sense? That would have made it harder because I have something else over there to worry about, something else to mess with. And so this is what you, if you will, mindlessly do. And in a sense, if you're, you made it this far in math, you should like this part, because it's like, that's what I've always done in math, is do the same thing to both sides. That just feels so much better. But again, what's really cool about this, like what's neat, what just happened there that's kind of neat, even though it looks weird a little bit, what just happened that's kind of neat, that wasn't neat back here? Not neat, neat.
You could plug in the initial values.
That's neat, but I'm looking for something. I'm asking you to read my mind. This was kind of ugly, and now it's not ugly. Well, it is in a way, but what isn't ugly about it?
There's only one derivative. Or no, there's no derivatives actually, because you evaluate that at the point. That's your initial condition. There's no derivatives.
That's exactly the idea. In other words, this was y double prime and y prime and then no derivative at all. And for that reason, I'm not able to add them, right? Because they're all different. But what happened to them once they got transformed? Bam, bam, bam. Does it make sense? They're all like terms now. They're all Laplace transforms of y. Like there's no more derivatives anymore. Like I can add them now. That's what's so cool about this. So for that reason, I'm looking at all those terms. So there's a couple things. One of you just pointed out, I think it was Raymond. There's a bunch of stuff we know. In other words, we know that y of 0 is actually 3, right? And we know that y prime of 0 is actually 4. So any place I see those, I can, put those numbers in. And so that's nice. And so those aren't terrible. But again, look what happens with all, and I kind of need those to go to the other side. Does that make sense? Like that 3, 4, and 3, like those are the non-Laplace transforms. So those have to go to the other side. So notice, and you can easily make kind of a dumb algebra mistake. It's like, yeah, that's 3, but there's still an s there, right? So when I add that to the other side, it's 3s. And this is a -4, really. So I'm going to add it to the other side, and it's going to be a +4. And then this is actually a 12, right? +12. So I got to subtract 12 over to the other side. So I kind of get all the non-Laplace transform stuff out. And then I'm just looking at, hey, look, everything's a Laplace transform, which means I can factor it out. And it leaves s squared there and -4s there and +4 there, which is something we saw the other day. But what's really wonderful about what that equaled? What is this guy that we've seen before? That's the auxiliary equation. So I mean, if this was a race, perhaps you can see, and it isn't, like if I'm you on a test, I would just write this all out every time. But that's what's going to happen every time. In other words, you can just look at that problem up there and you could immediately skip all this junk. You could just say, if that's true, then bam, I'm here. Like skip everything green, you're bam, you're right there. Now the thing you can't skip is like, what else was there, right? Like you gotta, but does it make sense? You could streamline this process if you wanted to.
That's cool.
Yeah, it's really cool. And of course, this is 3s minus 9. Wrong. 8. Good if your teacher could actually do basic math. And so, in my opinion, like as I've been sort of explaining, everything has been just wonderful and fun until now. Now's where the work starts. Basically, I have to rewrite the right side of that as a bunch of recognizable Laplace transforms. And if I can pull that off, then I'm good. Now, what we're going to see a lot, we've seen it every time in the 2 examples I did, and we're going to see it here again, is look at the denominator. It's s squared minus 4s plus 4. Interestingly, 3s minus 8, that does factor, but it factors to something unusual this time, because instead of like s minus 2s plus 3, It's s minus 2, s minus 2, right? So it's like junk over s minus 2 squared. And so I found myself thinking, was there something that looked like that on the bottom? So it's like, here's s minus 2, but not squared, right?
It's not sine up there.
And it's like, it's kind of here, right? It's there, but then there's this, plus b squared thing. And so, man, it's like, that was close. It's also here, except for there's again a plus b squared. And so, is there some way I could maybe make it look like that? Is there something I could do to make it look like that? Or is there other ones that are even better? What about that? If n was 1, wouldn't that be s minus a squared? That's interesting. Notice not this one. That's not the same, s, that's individually squared. Again, this, but like if I say s plus a squared, that's not equal to s squared plus a squared, but I'm just reminding you. So it's like that one's not right. Notice this is interesting. Like, what if this was like s squared plus bs plus c? Like, is there any, because that's what we have down there, right? Is we have this quadratic equation, like not even factored. Is there one of these that just has like everything, it has an s term and an s squared term and a constant term? Is there any of those that look like that? Notice like these two seem to only have like the two n terms, like they don't have this middle one. They don't have an s term in there. It's kind of interesting, isn't it? But it's like, no, there isn't. There's not.
We use the cosench one and then just have BB0 at the very bottom.
Yeah, that's interesting, isn't it? Cosine h, that's hyperbolic cosine. Could we use that one and just have BB0? What's your thoughts on that? So it'd be EAT. If that's 0, the cosine, we don't know what hyperbolic cosine is, but 0 times t is 0. So it turns out the answer to that is 0. Like the cosine, well, maybe the cosine of 0 is, actually I don't remember this, I better not overspeak. Remember how the cosine of 0 is 1? Maybe the cosh or hyperbolic cosine of 0 is 1. I'd have to look that up because I don't remember. Maybe that's 1.
It depends on if they're, never mind. That was, sorry, incomplete thought.
Notice what happens though if you let b be 0. What happens to the left expression that's left here?
Oh, it just becomes the one for e to the at.
Yeah, there's an s minus a on top and 2s minus a is on the bottom. Don't they cancel?
That's
and
awesome.
So it actually becomes e to the at. So based on what I just said, I think this does go to 1, even though I don't remember it. So notice like that didn't work, like it didn't help. It would have, because it went away basically is the problem. It disappeared. And so that kind of stinks. Interesting. But this one right here, I'd say is pretty hopeful. Do you agree with that? Isn't that what we got? Except for what's on top?
In factorial.
In factorial. So that, for us, it's 1. It's 1 factorial. Does that make sense? We don't have a choice. N has to be 1. So this can be s minus a squared. And that means n is 1. And so we need 1 factorial on top, which is just 1. And so that'd be great. If there was a 1 up there, if there was a 1 sitting up there, I'd be home free. Do you agree with that? Anyway, those are some preliminary thoughts. But again, our approach to this might be first try, and I'm going to actually write this word down, decompose. we're trying to decompose this fraction. So the fact that we recognize that this factored so there's two things I could do. One of them is I could say, well, then it would be a over s minus 2 plus b over, it's not a 2. Does it make sense? That would be the first thing that you would think to try. And you may remember from last week when we tried this with the Laplace transform. That's what we did. In other words, when we divided the junk, which turned out to be the auxiliary equation to the other side, and we had this sitting down here and we factored it. We said, oh, look, s minus 2, s minus 5. And then we decomposed it. We said, well, hey, that's a fraction having been added, so let's unadd it. And we said, okay, well, maybe it's a over s minus 2 and b over s minus 5. And then we went forward and it actually worked. That worked great. So then we're effectively trying the same thing today. But that should really bother you because, like, look what happens. I mean, if I try to add those by, multiplying this top and bottom by s minus 2, then don't I get a s minus 2a plus b s minus 2b all over the required denominator? So this looks to be working good. And so I just need to make this equal to my 3s minus 8, right? So we're doing great. I don't see any problem here. It looks like we're doing great. So doesn't that mean then, if I switch colors, that, well, there's 3s, so that would mean kind of this s term and this s term. So that would mean a plus b needs to be 3 to take care of the 3s, and so that's great. And then the constant, negative 8, comes from the two constants. There's a constant and there's a constant, no s term. So that means negative 2a minus 2b has got to be negative 8. Two equations, two unknowns. This is great. It's going to work awesome. So you might say, well, okay, I'll just do this by hand because it's so easy. I'll just multiply this by 2. So that becomes a 2a. And then when I add these, there'll be no a's. Awesome. But what happens that's not so good? Bam, 2b plus, oh no, there's no b's either. That's not good. And then 2 times 3 is 6. 6 plus negative 8 is negative 2. So unfortunately, when I put those together, I didn't get an equation, which basically means I don't know what to do. More importantly, it doesn't matter what a and b are, you're not going to get them to be negative 2. Does that make sense? Pick a and b to be anything you want, since they're both multiplied by 0. So this is impossible. Like, basically what it just means is this is impossible. Conclusion, bad guess. Your guess is bad. Just like it was a second ago. Like, remember, we tried and didn't work, right? We got to get better at guessing. This is what 7.4 is about. And so this is kind of weird. So what do I do? Like, and again, the only reason that happened is because it didn't just factor, it factored to the same thing twice. So that's a problem. That's a special case, if you will, of this decomposition, that I got to do this somehow differently.
You just throw in another a, s plus c.
Yeah, let's try something else. Let's try.
Maybe you'd have to do that with b also.
Yeah, so maybe. So, one option would be to, unfortunately, there's just a ton of options now. It's like, do I do that? Like, give the AS, and I stop there and try that? Or do I come in and, give it everything else too? In other words, I'd add an S term, so give it a constant. Would that work? Or do I have to actually go on and do that with the B as well? Would that work? Let's try that. Because remember, there's no reason C and D could pop out and be 0. Like just because I put them there, like if this works, then maybe they'll pop out and be 0. And so I don't know. Let's just try it. See what happens. So again, we've got to multiply. I'm just writing it here so that I can see. Oh, wait, they already are a common denominator. Why am I even doing this? Did you think about that? It's already a common denominator. Why do I need to multiply top and bottom by that? I did that last time and none of you chimed in.
I didn't notice.
I will admit that I didn't either. So I could just add these things right now. AS plus C plus BS plus D over S minus 2. Well, and part of it is like, that's not really good though, because didn't I need an S squared, S minus 2 squared on the bottom? So it's like I could do that right now, but I kind of need there to be an S minus 2 squared. So maybe I sort of have to do it even though I didn't need to. Let's see what happens. So, okay, let's not screw up the distributive law. AS times S is AS squared. AS times 2 is minus 2AS. C times S is C times S. And C times 2 is C times 2. And then we do the same thing with B. So I get plus BS squared minus 2BS plus DS minus 2D. All over S minus 2 squared. And so awesome. So the question is, can I get this whole mess to equal, what was it, 3s minus 8? 3s minus 8. And that feels, do you agree that that guess feels kind of huge? Like, man, that's gigantic. So, but you know, it's like, maybe it's gigantic. Well, notice there's no S squared terms. So that would mean those two. That means A plus B has to be 0. That's fine. That's great. There's all kinds of answers to that. So that just seems good. And then I'm looking at my S terms. So this is my S squared terms. Looking at my S terms, minus 2AS plus CS minus 2BS plus DS. That's all got to give me a 3. So that feels daunting because it's like 4 unknowns, right? So, and then finally my kind of my constant terms. I guess I'll say S to the 0. I don't want to say C because I C's on the other side. So S to 0, my constant terms, minus 2C and minus 2D. There's only 2 constant terms. Those have to be my minus 8. What's your first reaction, you Math 261 people from spring term, to this system of equations?
Make a big old matrix.
But we got 3 equations and 4 unknowns.
Yeah, the problem is to use that big matrix, we need 4 equations and 4 unknowns. And so this feels like it won't be, it doesn't feel like it won't be solvable. I mean, you need 4 equations and 4 unknowns, 3 equations, 3 unknowns. You know, then part of me thinks, well, okay, well then we threw too many unknowns in there. Like, let's not have a D. Let's just have three equations, but 4 unknowns. That's not going to work. Like, you're not going to be able to answer that question. So it sort of feels like, darn, man, that was close. Like, we almost had it. Don't you feel that way?
Could we just let D equal 0?
Yeah, let's try that. I was actually gonna
Then we could solve for
suggest
C right there.
I was going to suggest no D and then like start over, but maybe we don't have to start over. Isn't that a good idea? Like, let's just, if D wasn't there, then D would be 0, right? So I could actually just reuse this if I don't have to start over. If I just said, great, D is 0. Now it's only 2 different places. And so is that good? Now I have 3 equations, 3 unknowns. Awesome. So my first reaction to that is like, yeah, baby, we're on now. It's on. And I really like the third equation because I don't have to even do a matrix, because the third equation says negative 2c equals negative 8. So does it make sense? I know right now that c has to be 4. And then if c is 4, I have my top equation, a plus b has to be 0, but then my second equation is negative 2a minus 2b equals, and if c was 4, I'm just going to subtract it to the other side, so it'd be negative 1. 2 equations, 2 unknowns, awesome. Do you see the problem though? Well, the same thing's going to happen that just happened a second ago. In other words, if I say, oh, good, I'll multiply this by 2 and I'll add them together, well, you end up with 0a plus 0b equals negative 1. Again, impossible. Now, again, what I don't like about 7.4, why I'm not teaching it this way, you future math teachers, is 7.4 throws the techniques at you as to how to fix this problem, like helps you learn how to guess for this. And I get that, but they're throwing that to you before you've ever even made these. And also you feel like you're in this just sea of memorization when you really don't have to be. But the interesting thing is there's no way out of this. In other words, wasn't this a conundrum? Like, if you did not recognize that repeated roots was kind of a weird situation and do something different, then you're not going to get out of this mess. That's the problem. I mean, you have to recognize it here too. Like, we have to guess differently, thanks to the fact that both of the denominators were s minus 2 and s minus 2. We have to guess differently, and we tried 2 really good tries. I mean, I sort of felt really good about that last one, didn't you? And then bam, it just kind of went in the dirt again. So it's like, now what am I going to do? I mean, does anybody have any ideas? What can I guess now? Notice you can't let, just as a side note, notice you can't also let c be 0, because if you did that, then this right here would be gone. And then there would be no way to get negative 8. You wouldn't have any constants. Does that make sense? So we let d be 0 and that didn't work. We can't let d and c be 0. That won't work. So now I feel like, geez, what do I guess now? I don't even know what to guess.
Could you show the original equation again?
Yeah, so we're sitting here having kind of woefully failed at guessing.
You could do the repeated factor. You could do like a over s minus 2 plus b over s minus 2 squared.
Where are you coming with that from?
Well, first
it's okay
of all,
to be honest.
I read the book, and
Mhm.
I also kind of remember that from when we did it in calculus,
Yeah.
in Calc 2. But it does make sense, because if you had, because that would give you some 2 fractions that don't have a common denominator, but their common denominator would be s minus 2 squared.
Mhm. Yeah, so we'll get there. But what I'd like to try that, you know, in a sense, maybe I should have tried earlier is, isn't this one kind of what we're staring at? Like, don't we have that? If n is 1? So I just want to run down that trail for a second. So in a sense, we're taking a pause and just, you know, kind of feeling like, I don't even know what to guess now. David reading ahead, and also based on remembering some things from calc, because this is not the first time you've had to decompose things. Is telling us what is the sort of simplest or, you know, most mechanical kind of way out of this. But I'm just kind of curious. In other words, this business right here could decompose right now. In other words, couldn't I write it as 3s over s minus 2 squared, and then minus 8 over s minus 2 squared? Do you understand where I'm writing it like this? Because isn't that second one anyway exactly what this is saying? In other words, if n is 1, then that's 1 factorial, which equals 1. And if n is 1, notice over here n is 1, so that would be t e to the at. So don't I know one of those now, like, or at least part of one of them? That's kind of cool, isn't it? So all that to say, isn't this the Laplace transform of t? It was e to the at, but for us, isn't a2 positive 2? Because wasn't it s minus a? I forgot, I gotta look again. Yeah, s minus a, and ours was a minus. Therefore, this is a positive 2. So in a sense, it's like the opposite sign. So that'd be really easy to screw that up and go, oh, it's minus 2, right? No, it was s minus a positive a. And so since a is positive 2, then so it's like there, like that's kind of cool, right? And then there's just an 8 out in front of it. And that's true. And of course, that shouldn't surprise you, right? Because remember, back in the day, weren't we told to add a term like that to it? So, but that's kind of cool that just came out without us having to do anything. I think that's kind of interesting, isn't it? But what are we going to do with this guy? Is there anything that looks like that? Because notice in our problem, it was a constant that was up there, but we need something with an s up there. Like, is there anything that would? That's the wrong one. So I need the same thing, like an s minus a squared, you know, kind of a thing, except for I need an s on top. I don't want a constant on top. Notice these are close, but they're s squareds, like that's s squared, not s. And that's not good. And again, this is close, except for it's not s plus a squared, it's s squared plus a squared. And unfortunately, that algebraic distinction is profound. And so notice there doesn't seem to be anything that's, I mean, this has got a little potential, doesn't it? But again, in order for that to work, b would have to be 0, right? We saw that before. And if b was 0, then that makes it s minus a over s minus a squared. And if b is 0, cosine of 0 is 1. It just turns into the Laplace transform of e to the at. So that was close. It has an s on top, but it doesn't work. So, you know, is this a dead end? Is there like something I could do with this? So it does turn out that this is tricky, and this is why, again, I don't think the author was ultimately wrong to sort of throw 7.4 in there, because we really got stalled out here. But I just think it's important for you to, I don't know if suffer is the right word, but like feel the pain of this a little bit. You know, for me just to tell you, oh, if you see this, do it this way. I don't think that's a very fun way to learn, and it's certainly not something that's going to persist in you very long. But in a sense, I'm kind of in the same spot. In other words, I don't know how to fix that. I was able to kind of get part of this but I don't know what to do with that. So, you know, what do I do when this is repetitious, if you will? Are you feeling that in the sense that it's like when I say huh here, are you kind of feeling that like I'm out of good guesses? Like I don't even know what to try now. Like, didn't we try a bunch of things? And it's like, geez, what do I try now? So we just did sort of 3. Let's go try. I think you can do that with a V, but let's not.
Part of me wants to ask Siri. I remember you asked her something crazy one time, and she actually figured it out.
Yeah. How do you decompose 3s minus 8?
Well, not that. I bet if you just like, what's the Laplace transform of this? I wonder if she would know.
Right. And that's good because I think, I mean, that shows you're feeling the pain of this enough to sort of feel like a dead end, or, you know, I need a hint now. I mean, I need a good idea. And I love to distinguish in the learning of mathematics, the difference between a genius had to step in, because that happens a lot in math. A genius has to step in and come up with a really good idea. Whereas there's lots of things that it doesn't take a genius. Like you just have to be a little persistent and try a few things. And as I said, this is the true heart of mathematics. I think I mentioned before the book Mathematician's Lament, and this guy wrote a whole book around the idea that like what we're doing right now is mathematics. It's the fun of mathematics. It's like asking an interesting question and trying to figure it out yourself. The last thing you want if you're a true mathematician is to what he liked to call paint by numbers. In other words, you'll come up with a beautiful picture. It's just that like what's inside that little spot of 2, what color is that red? And then you paint it red just because you're being told what to do. And in the end, it's like, look at the painting I made. Well, you really didn't make that. Like somebody else told you what to do. And so it takes the fun out of it. Now, you know, in the end, it's like you're in this class because you want to be an engineer and you got to get the dumb class over. So we can't just sit here trying to create our own paintings forever, because real mathematics might take 6 months, might take 3 years to just to try to figure out a way to decompose this. But we could do it. That's the thing I want you to understand. We could do this.
I think there would have been a more perfect time for Landon to come in and be like, sorry, I'm late. Why is there a question mark there? And just give us the answer.
And I think that's one of the things that's really cool about this, because I'm not a person that would come up with the idea like left to myself. I mean, I already know it, so it's kind of, you know, cheating in my case. But it does take sometimes somebody who just sees things differently and has ideas where other people don't have ideas, you know. And I love that part of just being a human being. Even in business, you need people that just routinely show up to work every day and do their job to make the business run. But it actually takes kind of a crazy person who's always starting businesses to come up with that, and like they fail, their businesses fail, and they lose all their money and they make a big mess all the time. But they're like the creative types in the world, and you know, they're the ones that start the business, but they do need the ordinary folks that just kind of, you know, get the job done on a daily basis. And so interesting. Anyway. So David, what do you think the solution is to our mess? What do we need to set based on your reading in 7.4? What do you think we need to do?
So I think it should be a over s minus 2 plus b over s minus 2 squared.
And this harkens back to something we just did a minute ago, and I want to mention this. Our first problem of the day. Do you remember how we failed a little bit at our guessing here too when we had s squared on the bottom? Is that kind of what we have now? We have an s squared on the bottom, right? Except for it's not just s, it's s minus a squared. And so when we did that, what was our guess that worked? Because notice we don't need to really pay attention to this. We need to pay attention to what was our guess here. the book's solution to that, the generic kind of knee-jerk reaction solution to that could have been accomplished here too, is when you see that what's on the bottom is not to the first power. In other words, over here we had an s plus 3 and it's to the first power, and so we were able to just put a constant above it. If you see that this is squared or cubed or something worse than that, a simple guess up here really doesn't work quite so good. And the book's answer to this, I think I'll probably erase this, but just because it'll look confusing to anybody that looks at the notes later. But another option for this would be a over s squared plus b over s. In other words, that would have accomplished the same thing that what I, if you will, my guess accomplished. So as a, I don't know, a brilliant person stepping in, I don't know if brilliant's the right word. We might be able to get there too. But if you see that what's on the bottom is not just to the first power, then that's one way out of it. Because in reality, s was a repeated root. Does that make sense? And so, but my point is that's a much more surprising guess. I think that's why I sort of did this playfully. We got out of this mess by just adding stuff to this until we found something that worked. So we had to put something a little more complicated up there. And so I'm kind of wondering the same thing though with our problem. In other words, if we took the same approach to our problem, we said, well, what's down here is not s, but it's s minus 2 squared, right? Well, then could this be a times s minus 2 plus c or something like that? I mean, that's kind of how we got out of the mess before, right? And I actually don't know. So let's go try that before we sort of try the, now,
That would ultimately be our result if we found the common denominator. So I think it would work.
yeah, so let's try that first. But then here, like, we don't have anything to add it to. But do I need to? Like with this?
Right. If you just distributed that, you would be fine. I think.
That's kind of interesting, right? I mean, again, the book does not take this approach. It's not near as playful. I believe enough in that book that I read that I kind of like to try to mix some of that thinking in, just because it takes some of the, adds some fun to it. So that means the top would be a s minus 2a plus b, whoa, over s minus 2 squared. And so now do I have enough information to pull off what's sitting over there? And it's kind of interesting. Like I put s minus 2, but I don't. Could it be s minus c? Like, does that actually have to be a 2? I don't know. I mean, I'm just trying to use the pattern I used before. Let's just see what happens here. Again, it looks like it works because I only have one s term, and so that's the 3. So that means a's got to be 3, right? And then I have minus 2a plus b left to give me my constant, which is -8. And of course, since we know a is 3, that would be -3. I would add, I'm sorry, -6. Then I would add 6 to the other side, and b would be -2. So I guess what we're saying then is that 3s minus 8 over s minus 2 squared could be rewritten as a times s minus 2 over s minus 2 squared plus b over s minus 2, which is negative, b is -2 over s minus 2 squared. Did that do any good? Is that helpful?
I don't think so. Well, can you
Remember
cancel out
that,
one of the s minus 2s?
yeah, remember that this looked a lot like that Laplace transform of e to the, or like t e to the at thing. Remember there was just a 1 up there, but then over here aha, all of a sudden something wonderful happens, which is, yeah, I can actually cancel this and one of these. And so that just becomes 3 over s minus 2 squared. I think this is going to get us out of the woods. And this other one would be minus 2 times 1 over s minus 2 squared.
Isn't that first one 3 over s minus 2?
Yeah, it is. I just
Okay.
noticed that myself. That canceled. And so isn't this just 3 times the Laplace transform of e to the 2t? Isn't that what s minus 2, 1 over s minus 2 is? I'm going too fast there.
Yeah, that makes sense.
In other words, as a middleman, this would really be 3 times 1 over s minus 2. And remember, it had to be a 1 on top. And the same thing was true for this. So a second ago, didn't we say that this one then had to be, well, there's a minus 2 out in front of it, but minus 2 times the Laplace transform. What was that again? If I'm myself thinking, I don't really remember very well. It was like this, right? Let me erase all that and like start over because it's good for your brain. And so it's like, yeah, that looks like that as long as n is 1, which means there's a 1 on top. If n is 1, then that's t to the 1. And a is 2. Yeah, so it's t e to the 2t, right? So it actually was important to, if you will, throw that s minus 2 up there because it ended up sort of matching what was on the bottom, and so it canceled out. It's kind of interesting. I guess another way to think of this is, you know, is like some way to rearrange this. It's almost like we rearranged it like 3s minus 6 minus 2. That's minus 8, right? Minus 6 minus 2. Why did I do that? Because then if you factor a 3 out, you get an s minus 2. And then this s minus 2 can cancel with one of those s minus 2s. So this is kind of pretty tricky, right? It's like, man, I can see, yeah, this is going to be hard to be. So that's kind of cool. I mean, this is taking the same approach. So anyway, we're actually getting this answer then. So then we're saying, let's see, I kind of forgot even what the heck we were doing. I don't know about you, but Laplace transform of y equals all that. Okay, so we're saying then that the Laplace transform of y now equals 3 times the Laplace transform of e to the 2t minus 2 times the Laplace transform of t e to the 2t. And therefore we can say that y, after I take the inverse Laplace transform, y is equal to 3e to the 2t minus 2t to the 2t. I'll come back to that because I know I'm going away from that kind of fast, but you know, isn't that kind of what we ended up with up here? In other words, when we got repeated roots, there was just a normal e to the RT term. In other words, R is 2, but then R was 2 again, except for there was that added T, and we just have a couple of constants out in front. So it's like it ended up in the right form, didn't it? Like it, but we didn't have to know that. However, it wasn't like that was easy, right? Like repeated roots are still a problem. Like we really have to do a good job guessing. So that was much more creative. Now let's just take David's observation in kind of the book, and let's just see if this is a kind of a more systematic or better way to do this, and we'll be done. But like the book's approach from 7.4, so they would have taught us this, and so we're sitting here with 3s minus 8 over s minus 2 squared. And the important thing is over something squared. If the squared wasn't here, we're very happy. But when that's squared or cubed or something like that, I'm not happy at all. I'm really unhappy. So the book says an easier, more systematic approach to this is just to put it there squared and then just put it there without squared. And that way you can just have a constants on the top every time. Now that will work too. So, okay, what would that mean? Well, in order to have a common denominator, this would have to get multiplied top and bottom by s minus 2. Now they have a common denominator, right? And I can add them. So that means this would become a plus bs minus 2b over s minus 2 squared. What do you notice about that? Isn't that like kind of almost what we got? Like here. It's like it kind of produced that same thing. That's interesting. At least I'm just noticing that was familiar. So I'm there, except for this time I would say, okay, then the b has to be the 3. In a sense, I think I did it backwards, if you will. Like if I'd switched a and b on top and put the b over here and the a over here, I think I would have got the exact same thing, but it's going to result in the same thing. So bs, that's the only way we're going to get 3. And then it leaves a minus 2b has got to be the negative 8. And if b is 3, that leaves it negative 6. If I add 6, then a is negative 2. So then I can say that 3s minus 8 over s minus 2 squared is actually equal to a over s minus 2 squared, which is negative 2 over s minus 2 squared, plus b, which is 3 over just s minus 2. So I agree with the book. Like what you see in books is the distillation of some interested nerd spending days and weeks and months trying to systematize this and get it down to something that you can just mechanically do. And I think they're not wrong. It's just that for me personally, if you tell me this too soon, then I'm just not going to have a deep enough interaction with it to understand it. And I'm also going to be led to think I just have to give up. I can't think. I just have to do what I'm told to do. I have to walk down the path that previous hikers have set to walk to this waterfall. And I love this illustration. Should you walk down the path that is well traveled to the waterfall? Answer, probably, because that's going to be the easiest way to get there. Because people have done it lots of times before and they've probably sorted it all out. However, are there other ways? And might you see some beautiful things along that way? Yes. Will it take more time? Yes. But there's not just one way to hike to the waterfall. And that's kind of why I illustrated this. So, we're almost out of time and we'll pick it up there in practice tomorrow. We got more time. But in a sense, this is the fastest approach. If you see something squared on the bottom, and usually that doesn't happen. Remember, the only reason that happened this time is because we got it factored to the same thing twice. If it had factored to s minus 2 and s plus 5, we wouldn't have this problem. So basically the idea here is we like it when that's just a linear term down there. We do not like it when it's a squared term. That's the problem. If this is squared, we're not happy. Like we got to do something a little creative. We still have to notice, hey, this is unusual and guess a little more intelligently. That's the idea. So in a sense, this doesn't get us out of this conundrum. Like we still have to notice, hey, this is unique, right? We have to do something different in that situation. And of course, we're also wondering, like, how in the world would this ever happen? Like, if I get a complex, what does complex roots look like? Like if I'm trying to factor and, complex, how's that ever going to happen? And that's what we'll kind of pick up tomorrow. But I guess I would encourage you to kind of, study this a bit. Do you notice kind of in hindsight now that guess accomplished the same thing? In other words, the very fact that I threw an s minus 2 up there basically meant that this whole thing canceled and it ended up that. Does that make sense? In other words, it ended up with an s minus 2 on the bottom and an s minus 2 squared. And my guess is that's how the sharp people discovered it. But I think I gave you a shot today at recognizing the pattern, and I'll shut up after I say this, but we guessed our way. Wow, so long ago, I can't remember even where we were. I think it was the first problem we did. Sorry. Yeah, it's back here. We're getting close. We guessed our way here to the fact that this needed just more variables, right? So we ended up throwing a C in there. We said, we threw an S in because we saw that A and B didn't do it. So we threw an S in and that didn't do it. But when we threw this other constant, it did it. And so do you see how what we just did is kind of that pattern? In other words, what was sitting down here squared also had to be up there, but not squared. So there was an S minus 2 down there squared. And so we said, well, maybe if I put an S minus 2 up here, then it would work. And it did. Like, that's probably how this was discovered. I sort of gave you a shot at seeing that. And so, is there kind of a smarter way to write that down, or a faster way to write that down? Perhaps. But again, I think I've illustrated that Laplace is great in some respects, but it's not like just some automatic, easy way to do this stuff. But you should also recognize somebody has to work hard to make up a problem like this, like for there to be repeated roots. You have to try, don't you? So anyway, let's leave it at that. Really cool. Love hanging out with you guys. If you want to elaborate on any of this, feel free, but I was going to kind of give you permission to leave when the class is supposed to be over.
Is there a way to do Laplace transformations without partial fractions? Is there like an extra method?
I assume that by that you mean when you get to kind of here.
Yeah.
Yeah. I mean, the question is there some, even like a computer program? I mean, that's the part that's interesting in the world you and I live in. Like if that does decompose into something, is there some way to kind of just plug that in and have it, decompose it for us automatically? Kind of a quadratic formula, if you will, of decomposition world. Quadratic formula, we just stick in A, B, and C, and then bam, out pops the answer. So is there some kind of a, systematic way to do this? And in a sense, there is. But I mean, I think you could probably write a program to do that. But my question is, would it have to recognize, I don't know if you know anything about programming. I don't know much, but the concept that it would have to like check right at the start, what kind of when I try to factor this, what's going to happen? Yeah. Is it going to factor to two separate terms? Oh, if that's the case, then go do this. And then in our case, it factors to the same thing twice. Oh, if that's the case, then your program needs to, because like an if statement, if this is true, then go do this stuff. If something else is true, then go do something else. And then of course we haven't even tackled like, how does something factor to imaginary answers? Like, what does that mean? That was like a third case that caused sines and cosines to show up with the e's. So in some respects, I think you could do that, but whether it's a program or not, it's sort of left to us to kind of recognize that. Mm-hmm. It's almost kind of the same as the previous chart in the sense that, if I find myself thinking, well, I'll put the auxiliary equation into the quadratic formula. And if I get two distinct answers, then I'll do this. If I get repeated answers, I'll do that. If I get imaginary answers, then I do something totally different. So it's almost like, should I be using the quadratic formula to kind of check, where this is going to go? You can see that left to ourselves, this is a month-long experiment, which, and I actually would, for those of you that left, by the way, highly recommend reading that book. It's something, it's really thin. It's like a quarter of an inch thick, and it's actually small size-wise too, and it has big font in it. But mathematicians lament, and as a mathematician, he laments the fact that we just don't take the time to let people enjoy the fun of solving a problem. And as a teacher, I've put a lot of thought into that. But you can understand, practically speaking, if I said, hey, let's all, go rent a sailboat and we'll hang out in the lake and we'll stay there for 6 months and like figure this out. It sounds kind of fun, but it's like, yeah, but I can't do that. I have a job. I have other classes
right
I have
one?
to pass. And
It's by Paul Lockhart.
yeah, Paul Lockhart.
Okay. I think I might read it.
I'd highly recommend it. It's a short one, and it's I actually don't ultimately know what his conclusion is. He really kind of lambasts education, but you can't be serious that somehow we can help people, become an engineer, which is your real goal, perhaps. I don't know. In my case, as an educator, I just try to mix it in some and try to build in some time. And also I try to, I don't know if fake is the right word, but I try to fake that I don't understand what to do sometimes. I'm just like, I don't know, what should we try? And I'll take your ideas. Like I'll do what you guys say and we'll just try it. It's like fun to run down that road and see that it's like, well, this trail to the waterfall ends in a cliff. And so,
Yeah.
that's not good, but it's like, that's the fun of it. And I don't know, like for me personally, like if I go someplace, I usually don't like to have a tour guide because I'm listening to their same exact speech and I'm following this routine path. I love to just wander off and, discover stuff myself. It's just so much more fun. But I'm in the same boat. I mean, I like math, but I don't know if I like it as much as he does. I mean, I look outside and it's like, oh man, there's no smoke today. And I don't think I'm gonna play around with second order differential equations. I think my kayak is on top of my car right now. I can go to the river. That's what I'm gonna do. So I'm only a partial mathematician.
All right. Well, I'll see you tomorrow, Doug.